Hello, my name is Antonio Jurado, and I'm going to explain how to control a water level system using data reconciliation and virtual sensors. Here we have the table of contents. The first point is a description of the two-tank water system. The second point is an analysis of the closed-loop simulation. The third point is a virtual sensor 1 with solution 1. The fourth point is a virtual sensor 1 with solution 2. The fifth point is a virtual sensor 2. The sixth point is a comparison between reconciliated and non-reconciliated data. And finally, the point number 7 represents the final conclusions. The following picture shows the two-tank water system made of an upper water tank and a lower one. The aim is to control the water level in the upper tank. This diagram represents the two-tank water system with all its components. Both sensor 1 and 2 measure water height in the upper tank, but sensor 1 with high precision and sensor 2 with low precision. Sensor 3 measures water level in the lower tank with low precision. Sensor 4 gives the sum of the two levels, which is always 10 units. The motor pump can get a maximum of 15 volts. This is the Simulink model used to get a water level of 6 units in the upper tank. A first-order transfer function is used to simulate the water level behavior in the upper tank. There is a proportional controller. The real virtual sensor switch allows us to change between real or virtual data. The other switch enables us to choose either virtual sensor 1 or 2. This is the Simulink block used to simulate the 4 sensors. The signal acquisition system has a sampling time of 0.01 seconds. Data from sensors 2, 3, and 4 is stored into the matrix Y in the workspace. Taking into account that we are getting real data from sensors, the following picture shows the results from a 10-second closed-loop simulation, where the yellow line is the set point, 0 units from second 0 to 5, and 6 units from second 5 to 10. The purple line is the voltage applied to the motor pump, which has reached a maximum of 15 volts for half a second and has stabilized at around 0.7 volts. The blue one is the water level in the upper tank, which shows a stabilization time of 2 seconds with no overshooting. Let's imagine sensor 1 fails, shall we? In that case, this Simulink model uses a virtual sensor which substitutes the sensor 1. This virtual sensor 1 has been implemented by a Matlab function which provides the data from sensor 2. The following picture shows the results from a 10-second closed-loop simulation where virtual sensor 1 with solution 1 is used. The yellow line is the same set point, 0 units from second 0 to 5 and 6 units from 5 to 10. The purple line is the voltage applied to the motor pump, which has reached a maximum of 15 volts for half a second and has stabilized at around 0.7 volts. But in comparison with the previous one, it has bigger oscillations. The blue one is the water level in the upper tank, which shows the same response, a stabilization time of 2 seconds with no overshooting. This Simulink model uses the same virtual sensor than before, but it has been implemented by a Matlab function which provides the subtraction of data from sensor 4 minus the data from sensor 3. And that's the reason why it is called solution number 2. The following picture shows the results from a 10-second closed-loop simulation where virtual sensor 1 with solution 2 is used. The only difference in comparison with the first solution is the voltage applied to the motor pump, which has slightly smaller oscillations. Can we improve the system's response? The answer is yes. Let's have a look at this virtual sensor 2, shall we? This Simulink model uses a virtual sensor implemented by a Matlab function which provides reconciliated data from sensor 2. The A and V matrices used to get reconciliated data from sensors are shown in the Matlab program at lines 2 and 3. The following picture shows the results from a 10-second closed-loop simulation where virtual sensor 2 is used. The only difference in comparison with the virtual sensor 1 is the voltage applied to the motor pump, which has smaller oscillations. This response is quite similar to the first one where real data was used. This improvement has been possible thanks to data reconciliation. If we compare non-reconciliated with reconciliated data coming from sensors 2, 3, and 4, we can see how its quality has increased significantly. Finally, this slide shows the following 3 conclusions. The first one: the use of a virtual sensor can solve the problem of a defective sensor. The second one: reconciliation can improve a signal quality. And finally, the third one: a virtual sensor using reconciliated data is a powerful solution to a sensor which fails.